welcome to Talk Tensors.
Glad to be here.
So imagine looking at your phone right now. You instinctively know where the search bar is, right?
Oh, absolutely.
You know how to swipe down to refresh a feed, or what that tiny kind of ambiguous magnifying glass icon in the corner actually does.
It's completely second nature to you.
Exactly. You don't even think about the physical act of tapping the glass or the spatial geometry required to, move your thumb to that exact coordinate.
Right.
But for artificial intelligence, operating a mobile device just by looking at it has been this, almost insurmountable hurdle.
It really has.
It remains one of the most stubborn roadblocks in the quest to build true, autonomous, multimodal agents.
And the difficulty really stems from a fundamental disconnect between semantic understanding and spatial execution.
Okay, unpack that a bit.
Well, we have these large language models that can digest a complex code base or write a sophisticated essay in seconds. But we'll cover how this agent perceives visual elements in a zero-shot manner without any backend data. We'll analyze its iterative reasoning loop, its ability to self-correct in real time, and, the impressive benchmark results that prove it actually works.
Okay, let's unpack this, because to really grasp the significance of mobile agent, we need to examine why existing models couldn't simply do this out of the box.
Right, the historical context.
Yeah, which brings us to the vision-action gap. So you look at state-of-the-art vision language models, or VLMs, like GPT-4v, their semantic reasoning is flawless.
Absolutely.
Feed GPT-4v a screenshot of a mobile browser, and it can analyze the layout, read the text, and tell you precisely that you need to click the blue submit button to proceed.
It understands the functional intent of the UI perfectly.
But semantic understanding does not automatically translate to physical agency.
No, it doesn't. The VLM suffers from a massive blind spot, which is a severe lack of precise localization.
Meaning it can't point to it?
Exactly. It can identify the submit button conceptually, but it struggles massively to output the exact X and Y screen coordinates required for an automated script to actually execute a tap.
Like an Android debug bridge command or something.
Yeah, exactly. It just can't pinpoint that specific cluster of pixels.
I think we need to break down the why here, because it speaks to the underlying architecture of vision transformers.
It really does.
When a model like GPT-4v ingests an image, it doesn't process it as continuous visual field, right?
Right. It slices that screenshot into a grid of tokenized patches.
Like maybe 14 by 14 pixel squares.
Yeah, something like that. And as those patches pass through the self-attention layers of the transformer, the model is building semantic associations.
Right.
It learns that this patch containing a curved line is part of a C, and this patch with blue pixels is part of a button.
But through the pooling layers, the strict coordinate geometry gets lost.
Yeah, the exact absolute position of those pixels gets abstracted away. The model essentially trades spatial precision for semantic comprehension.
That makes sense. It's an architectural trade-off.
Completely. The model is optimized for visual question answering, not coordinate regression.
So it's trained to answer what is in this image.
Right, rather than at what exact pixel coordinates does this specific object begin and end?
So historically, researchers attempting to build mobile agents just decided to bypass this architectural limitation entirely.
Yeah, they cheated. Structurally speaking, they cheated by relying on the underlying system files.
Right, the metadata approach.
Yeah.
For Android testing frameworks, developers would hook into the UI automator and pull the Android application XML files.
Or for web-based agents, they would parse the HTML metadata.
Wait, isn't that like playing a video game by reading the source code instead of looking at the TV?
That is exactly what it is like.
It completely defeats the purpose of vision.
It does. They essentially turned a visual problem into a text parsing problem.
So the agent reads the XML, finds the node labeled submit button, and just reads the exact bounding box coordinates hard-coded into the layout file.
Exactly. It never actually has to see the button.
But that has to be incredibly limiting, right?
Oh, it's incredibly brittle in the wild. Relying on metadata means the agent fails the second it encounters an app that restricts access to those files.
Oh, right. Due to privacy or system permissions?
Exactly. We see this all the time with modern app development. Banking apps use security flags that blank out screen captures and block XML dumping.
To prevent malware from scraping account numbers, right?
Yep. Or think about mobile games built on engines like Unity. They don't use standard Android UI widgets at all.
They render the entire screen as a single custom canvas.
Right. So to an XML parser, a complex 3D game interface just looks like one giant blank square.
That's hilarious. It just sees nothing.
Literally nothing. Not to mention DRM-protected media apps or just poorly coded legacy apps where the XML tags don't match the visual rendering at all.
Which is exactly why the paradigm shift presented by Mobile Agent is so critical. This is the breakthrough.
Yes, a purely vision-based solution. No XML, no source code, no system hacking.
It relies exclusively on screenshots of the device.
Right. By forcing the system to rely solely on RGB pixel data, the raw visual output of the screen, the architecture becomes universally applicable.
Because it fundamentally ignores how the application was coded.
Or what engine rendered it, or what security permissions are locking down the backend. If the pixels are visible to a human user, they are accessible to the agent.
Okay, so logically that connects to the next big question. If the AI can't read the code to find the buttons, how exactly does it see where to tap?
That is the big technical hurdle.
Yeah.
If the VLM can't reliably guess the X and Y coordinates, how do we give this agent the precise localization it needs?
Right. Giving the agent eyes, essentially.
Exactly. So the researchers engineered a dedicated visual perception engine to bridge this gap.
And it uses two distinct visual perception tools to map the screen, right?
Yeah, separating the task into two distinct pipelines: text localization and icon localization.
Okay, let's dive into text localization first. How does it handle OCR, or optical character recognition?
Well, rather than forcing the VLM to guess coordinates, the system delegates the spatial mapping to an external OCR module.
So when the agent's reasoning loop decides it needs to interact with text, it outputs a command like, click the text settings.
Right. And then the OCR tool scans the raw screenshot to find the bounding boxes for that specific string.
But OCR isn't perfect. I mean, especially on mobile environments with highly stylized fonts or low contrast text.
It's far from perfect. So the architecture actually accounts for this friction by breaking down the OCR process into three fascinating scenarios based on the agent's query.
Okay, what's the first scenario?
The first is when the OCR returns 0 instances found.
0 instances. Why would it ask for text that isn't there?
Because the agent hallucinates.
Of course.
Even the most robust multimodal models will hallucinate UI elements based on their training priors.
Right, so if it's on a new shopping app, it might just assume there's an add to cart button.
Exactly. It confidently requests to click add to cart, but maybe the specific app actually uses the phrase place in bag.
So the OCR scans the screen, finds no add to cart string, and flags the failure.
Yes. The system intercepts the action before sending an erroneous click command. It forces the agent to try a different operation.
It acts as an internal circuit breaker? That's smart. What's the second scenario?
The second scenario is the easy one. 1 instance found.
Oh, perfect. The agent requests settings. The OCR finds one bounding box for settings.
The system calculates the center coordinates of that box and executes the click. Clean and deterministic.
But mobile screens are dense. What if the text shows up more than once?
That's the third scenario, and this is where the engineering gets really clever. Multiple instances found.
Yeah, like if there are too many instances like the word Z on a news app.
If it's a ridiculous amount of instances like the word the, it just flags it and asks the agent to re-strategize entirely.
But what if it's just a few? Like the word economy and a section header, a headline, and a navigation tab?
Right, the multiple instance problem. A standard script would crash or just click the first one it finds.
This is probably the wrong one.
Exactly. So what Mobile Agent does is it translates the spatial coordinate problem back into a visual semantic problem.
How so?
It physically crops those sections of the screenshot. It preserves a small margin of the surrounding visual context, and then it draws thick, highly contrasting red boxes around these cropped areas.
Wait, it actually draws on the image.
It draws on the image, it numbers each red box, stitches them into a new composite image, and feeds that modified image back into the VLM.
With a prompt asking which red box do you want?
Precisely. Which of these numbered regions corresponds to your intended target?
Oh, wow. That is brilliant.
By doing this, they completely bypass the VLM's weakness with coordinate regression.
It doesn't need to know the pixel location. It just needs to recognize that box number 3 has the word economy next to the stock market photo it wants.
It turns localization into a multiple choice visual question answering task, which is where VLMs excel.
Using classic computer vision to draw a map, and then asking the LLM to read the legend. I love that.
It works incredibly well.
But okay, text is one thing. Text is structured. What about all the ambiguous little symbols on our phones?
The icons.
Yeah, how does it know what a like button looks like? Or a hamburger menu? There's no text string for OCR.
That brings us to the icon localization pipeline, finding shapes and colors.
How does that work?
It requires a dual model approach. When the agent wants to interact with an icon, it is forced to describe the icon it wants in text.
It can't just say, click the user profile.
No, it has to be a visual description, like white heart icon or a circular icon with a silhouette of a person.
Okay, so it bridges the functional intent with the physical parent.
Exactly. And once it has that descriptive string, the system uses a detection model called Grounding Dino.
Grounding Dino. That's an open set object detection model, right?
Right. Unlike traditional models that only know specific classes like car or person, Grounding Dino leverages language to detect arbitrary objects it has never explicitly seen before.
So it identifies every single distinct graphical element on the screen that might be an icon.
It generates bounding boxes around all the candidates.
Which probably leaves you with dozens of bounding boxes.
Oh, tons of them. So to filter that down to the single best visual candidate, the system uses a similarity model called CLIP.
CLIP, Contrastive Language Image Pre-training.
Yes. CLIP projects both text and images into the same mathematical space. It understands that the text embedding for magnifying glass and the image of a magnifying glass are mathematically similar.
So it matches the agent's text description to the best visual candidate cropped by Grounding Dino.
It calculates the similarity score, ranks them, and the bounding box with the highest score wins. The center coordinates are calculated, and the click is executed.
That is a lot of compute overhead, but the accuracy must be fantastic.
It is. But simply being able to point at a screen doesn't make you intelligent.
Right. Pointing is useless if you don't have a plan.
You need a brain to orchestrate those clicks.
Which leads us to section 3, the iterative brain, the self-planning and orchestration layer.
The cognitive framework of mobile agents.
Right, so they use an iterative self-planning loop inspired by the React prompting format.
React meaning reasoning and acting.
Yeah, so for every single step, the agent must output an observation, a thought, and an action.
It forces a structured chain of logic instead of just spitting out a massive, brittle script of steps.
So the observation phase, the agent has to explicitly state the facts of the current visual state.
Grounding the model in the immediate visual reality. I am on the home screen. The settings app is visible.
Then the thought phase is the inner monologue.
Right, processing the logic. I need to open the settings app to access display preferences.
And finally, the action phase, the command sent to the device. And this involves a strict action dictionary.
They drastically restricted the agent's action space. It is only allowed to use 8 core operations to interact with the world.
Here's where it gets really interesting to me. What are the 8 actions?
Open app, click text, click icon, type page up, page down, back, exit, and stop.
By limiting the agent to just 8 basic human-like inputs, you prevent it from getting overwhelmed by endless API calls.
Exactly. You prevent a combinatorial explosion.
It's using the exact same toolkit we use, just taps and scrolls.
If you let it calculate precise vector math for every swipe, it would waste all its compute on geometry instead of semantic goals.
Let's walk through a concrete example of this execution loop in practice from the testing data. Navigating to a nearby gas station.
This is a great example. So the user says, navigate to a nearby gas station. The system captures the home screen.
Observation. I see the Maps app.
Thought. I need to open the app to search.
Action. Open app, specifically Maps.
Right. And the system executes that, and the Maps app launches. Then a new screenshot is captured.
And the loop repeats based on the new visual context and the history of operations.
Observation 2. The Maps app is open. There is a search bar.
Thought 2. I need to input my query.
Action 2. Click text on search here.
Then the keyboard pops up. Another screenshot. Thought 3. Type gas station. Action. Type. It's so elegant.
It iterates step by step, relying purely on the visual feedback of the previous action.
But wait, I have to point out a major flaw in this perfect logic. What happens when the agent inevitably makes a mistake?
Because real UI environments are hostile.
Yeah. What if it clicks a button that does nothing? Or an ad pops up?
If it blindly followed the loop, a single misclick would derail the entire objective.
So we need a safety net.
Exactly. Which is the self-reflection module.
This is what separates a rigid script from a truly autonomous agent. It can correct its own mistakes.
And this self-reflection kicks in under 2 specific conditions, or failure modes.
Let's look at condition 1, the invalid operation. There's a scenario from the testing data where the agent opens Google Chrome to find out the score of a Lakers game.
Right, so it observes the Google homepage, sees the search bar, and its thought process says, I need to type Lakers game result today.
So it tries the type action. But the keyboard isn't active because it hasn't clicked the search bar yet.
It tries to type into a null space.
In a normal script, fatal timeout error.
But here, the system feeds the agent the new screenshot post-action.
And the agent's observation notes that the screen hasn't changed at all. The keyboard isn't there.
Its thought realizes the error. The input box was not activated.
Oh, that's so cool. So it deduces the mechanical rule on the fly.
Yes. Its next action corrects it by clicking the search text first. It brings the box into focus, the keyboard appears, and it proceeds.
That dynamic adaptability is amazing. What's condition 2?
Condition 2 is the premature stop.
Oh, dealing with LMs satisficing. Doing half the job and giving up.
Exactly. When the agent selects the stop action, the system forces it to do a final audit against the original user instruction.
Did it actually finish the job, or did it just finish the first half?
Right. It compiles the final visual state and the instruction and prompts the agent. Evaluate the current state. Is the task completely fulfilled?
So if you asked it to leave a comment on a video, and it just found the video but didn't comment, the audit catches it.
It notes the absence of the comment in the UI, overrides the stop command, and forces the agent back into the loop to finish.
So we now have an agent that can see, plan, and correct its own mistakes.
Yeah.
But how well does it actually perform in the wild?
They put it through a really rigorous testing framework.
Testing the agent in the wild. Let's look at the benchmarks.
They used a comprehensive benchmark across 10 mainstream apps.
Not toy apps, like Alibaba, Amazon Music, Chrome, Maps, TikTok, and YouTube.
Apps with dense UI, constant updates, and ambiguous icons.
And they broke this down into 3 difficulty levels.
Simple tasks, right?
Yeah, level 1, simple tasks like download an app, direct and unambiguous.
Then level 2, complex tasks with added constraints, like swipe videos on TikTok and comment on a pet video.
That requires analyzing the video stream, finding an animal, pausing, locating the comment icon, and typing. Very complex.
And level 3 was abstract instructions. I want to relax. Find an app to help me.
Completely ambiguous. It has to decide what relax means, choose YouTube or music, and search for content autonomously. So what were the in-depth results?
They tracked success rate, completion rate, process score, which is the accuracy of individual steps, and relative efficiency compared to human steps.
And the numbers are staggering, frankly.
Over a 90% completion rate on simple tasks.
Which is great. But even on complex and abstract tasks, it was over 80%.
Over 80% completion on those highly complex multi-step constraints.
Furthermore, it operates at roughly 80% of human efficiency.
Meaning it takes a slightly more circuitous route. It explores, uses the back button, makes mistakes, but recovers logically.
It behaves like a human encountering a new app.
Yeah.
But I want to talk about the emerging capabilities, the wow factor.
The behaviors it was never explicitly programmed to perform?
Yes, the multi-app tests. The agent can look at the weather app, memorize the 5-day forecast, open the Notes app, and write a temperature analysis.
It maintains memory across app boundaries. To an API-driven agent, that's a nightmare of backend data passing.
But to this agent, it just reads the screen, holds it in its context window, and types it somewhere else.
Because the whole device is just a continuous visual stream.
And you mentioned 2 wild curveballs from the data.
Yeah, the first one is the poker game.
Because it's purely visual, the agent successfully played a game of poker just by reading the visual rules.
They used a proprietary poker app with a custom engine, no Android buttons, just visual cards and chips.
And it played multiple hands just by looking at the shapes.
It proves the visual perception engine isn't overfit to standard UI. It can parse novel, custom environments.
And the second curveball.
It effortlessly navigated Chinese language apps despite primarily being an English-instructed model.
Wait, really? It just did zero-shot translation?
Yes. The OCR extracts the Chinese text, passes it to the LLM, which has massive multilingual pre-training, and it translates it on the fly.
It integrates it into its English reasoning loop and executes the task. It's a universal translator for graphical user interfaces.
Without a single modification to its core code.
So what does this all mean for the listener? What is the ultimate so what here?
It is a massive paradigm shift. Because this architecture is purely vision-based and language agnostic, it doesn't care about the operating system.
It doesn't care if it's looking at Android, iOS, Windows, or a proprietary smart TV.
It eliminates the need for system-specific customizations. You don't need a Swift version and a Kotlin version.
If a human can do it by looking at a screen, this agent can do it.
It democratizes automation by circumventing the backend entirely.
Which leads perfectly into our signature novel notions segment.
Oh, I'm ready.
And just a reminder to you, our listener, this segment is for entertainment purposes only. This is where we pitch plausible yet outlandish research ideas based on the paper.
What's your pitch?
Idea 1, the infinite QA phantom.
Okay, I like the name.
I'm pitching deploying this exact visual agent architecture, not as a personal assistant, but as an autonomous QA quality assurance tester for indie developers.
So that makes a lot of sense.
Because it doesn't need back-end hooks. You just point a camera at a prototype physical device.
No brittle DOM integration tests.
Exactly. The agent endlessly explores untested apps, actively tries to break the UI by misinterpreting visual cues.
It stress tests the human-computer interaction design itself.
Right. And when it crashes the app, it doesn't output a hex code. It opens the phone's native Notes app and writes up its own bug reports based on what confused its visual reasoning.
It replaces manual app testing entirely. I honestly wouldn't be surprised if tech conglomerates are already building this.
What about you? Give me idea 2.
Idea 2, the cross-ecosystem MetaGhost.
The MetaGhost.
It's an extension of the paper's multi-app capability. Imagine scaling this to a multi-device capability.
Oh, I see where you're going.
A single cognitive agent that watches your desktop monitor visually, notes an urgent email, and then shifts to a virtual mobile phone instance to text you a summary.
So it jumps from Windows to Android.
And then it uses a visual feed of your smart home app on an iPad to turn on your living room lights as you get home.
Because it only relies on pixel inputs, it perfectly bridges completely closed hardware ecosystems. Apple, Windows, Google.
Without needing a single API key, it's just a ghost in the machine using the universal language of sight.
That is incredible. And I want to leave you, the listener, with a final provocative thought to mull over.
What is it?
If AI agents are going to navigate purely by looking at the screen, will the UI designers of the future start designing interfaces optimized for the eyes of AI rather than human eyes?
That's a fascinating thought. High contrast semantic markers instead of pretty drop shadows.
Exactly. A completely parallel visual language. Something to think about the next time you're frustrated by a mobile app's layout.
Absolutely.
Well, the link to the original Mobile Agent paper is available in the show notes below. Thank you for joining us on Talk Tensors, and until next time, keep unpacking the future.